It's a good question. It depends a lot on the use case and how people want to use the car. If you ask people how they want to use their car, then usually their answer would be, I want to use it in the same way as I use my combustion car nowadays. If you ask people who already have an electric car and how they are using it, then it's actually different from that. And most people who have the opportunity to put the car on their own driveway will charge almost every night. So if you look at that user group, then I think you need the amount of range that equals 1 day of usage. And then if you come back home or wherever you arrive, that's where you want to plug in. And the increasing fast charging infrastructure will mostly be used by most people, is mostly used for long trips. If you go on holiday or if you need to make a very long trip across the country. So how much range do you need then? Well, it differs a lot per use case. But I think it should be about what you would drive typically in your most extreme day in 1 day. And then you have most of it covered. If we look at the use case for people who don't have their own parking spot, and not many EVs are currently sold to those people who have to rely on public charging infrastructure, then it's going to be a bit different. So and a bit more difficult. They maybe would want to charge just once a week or something like that, if you can't plug it in on a daily basis easily, and then you might need more. You might need more range. I think I don't have an answer. I think because it really differs. It really differs for these user groups. For me, I have a Tesla Model 3 currently, and it does about 300 something kilometers, and for me that's more than enough. My co-founder Lex drives the same car. He needs at least twice that, just because of his usage pattern and how well he plans. I plan ahead very, very well. So when I left to come to Delft, my car was full. Lex would figure out 5 minutes before, oh shit, I have to go to Delft now. Oh shit, I went yesterday to here and here, so my car's empty. What do I do now? So it's so dependent on the people and their use case. I don't think there is an
optimal one size fits all.
There is no one size fits all range. That's it. I think you can devise different groups, and one group would need 300 kilometers. One group would maybe need only 100 kilometers, like the secondary cars that you only use for shopping. One group would need 2,000 kilometers, and it wouldn't be enough. And then the most interesting part is before we even get to that point, I think the other trends will converge. So the combination of robotaxis and the introduction of the robotaxi. And there, range is an entirely different concept again, because then you need to look at what's the peak usage, because then my entire fleet will need to be busy. So I need to cover the peak use period. And then I can use part of the fleet to charge and part of the fleet to drive. So if I have like a morning traffic peak and an afternoon traffic peak, then I would just need to bridge those. How many kilometers can you drive in a couple of hours? I don't know, a few hundred, so something like that. And in some regions, it might be more like San Francisco or something like that, where it's less morning and afternoon and more flat over the entire day. Then you would need to cover the entire day, so we need like 800 kilometers or something like that. So it's so dependent on the use case. I think that's also an interesting part. I think we should, once we go sharing, we can start to design the car specifically for the use case. And then it becomes, then we can start to give some real answers to this question. We talked about it in the early days. There's just a lot of issues with it in terms of logistics, getting the battery to the same place. I think without standardization across manufacturers, battery swapping is going to be hard, but maybe not undoable. The main challenges are also, for a big part, in how do you handle the warranty and whose pack is it, and do you lease the pack or do you buy it? And then if I bought it and they are swapped, how do I know that that the pack that I get swapped gets swapped in has the same quality and the same state of health? it's still quite a challenge to determine state of health of batteries. So there's just lots of issues with it, and I don't think anyone has really solved them. And then, of course, if we look at it from a business perspective, we had Better Place. We have Byton now saying they will. Oh, sorry, not Byton. NIO, right? Who's doing it? NIO. Yeah. So we have NIO saying they'll implement it. So I'm really curious to see how it goes. Currently at Lightyear, we don't have any plans for it. It might be a different case in different use cases. So if we for cars that are privately owned, I don't think there's a huge argument for battery swaps. In shared fleets, it might become a different question again. We might need to revisit it. So for the Lightyear 1 that we're currently building, so the 1000 exclusive series Lightyear 1 cars, the maximum charging power is about 60 kilowatts or 1C with a 60 kilowatt hour battery. And for that car, there are no plans to go any further. There's a couple of reasons. First of all, we hate that everybody is measuring charging speed in kilowatts. We think you should be measuring charging speed in kilometers per hour. How much range do you get for each for each hour of charging? If you apply that to the Lightyear 1, you compare it to a typical EV that has about twice the energy consumption, then with the same charging power, the Lightyear 1 would charge twice as fast in terms of kilometers per hour. So that's one thing for us to improve charging speed. We shouldn't improve the power, but we should improve the efficiency of the car. Then second of all, if you have a car that has a long range, that has, let's say, so for the Lightyear 1, we have about 725 kilometers of range, which even if you're driving 130 on the German Autobahn, or maybe even a bit faster, you still get 400 kilometers. After those 400 kilometers, you will want a short break, and I don't think it really matters if you then charge in 15 minutes or in 12 minutes. So improving the charge power even further from that point on, I think it might be useful for some people and in very specific use cases, but you have to consider the trade-off. Because if you want to increase the charging power even further, you have to switch to different battery cells that are able to handle these higher charging powers, which will get you a lower energy density, get you a heavier car, get you a less efficient car. More expensive and to drive and also less range, basically. Or it would become even more heavier to compensate for the range, and then charging would be slower again. So you have to consider the trade-off. Also, if you look at the cooling system, the 60 kilowatt fast charge power for the Lightyear 1 currently is already the most heavy use case, the heaviest load case for the thermal system on the battery. So like accelerating very fast, driving very long on the highway, that's all less load on the battery than the fast charging. So since the fast charging is the heaviest load case, it's also the limiting of the thermal system. So if you increase the charge power, you will have to increase the thermal management system as well. So I think you have to be very careful with making the trade-off and just increasing charging power, because you have to keep in mind what you're doing to the rest of the car. And I think that's sometimes not looked at enough. For Lightyear, it's also, for a big part, we want to achieve a very efficient car. And yes, batteries are important there, but they're not that crucial. So the energy density of the batteries is important. But the amount of R&D you would have to do to improve on that yourself is so ridiculously high that we can gain much more by just optimizing the aerodynamics a bit further in terms of how much money we would have to invest and the benefits we would get out of that. So that's why Lightyear is currently buying the batteries. And that means we're just comparing from all the different suppliers who can achieve the highest energy density and what's the best package for us, also in terms of lifetime, cost, etc. And the NMC cells that we are using currently, they're 21700 NMC cells. They came out on top in that comparison. There's no fundamental reason for us to choose for a certain chemistry except to look at the final output parameters, and currently NMC comes out on top in terms of what's available. If we would investigate or invest in the R&D ourselves, then well, like everybody's doing, we would of course also be interested in trying to get as much of the cobalt out, etc. Right now we're just we're more waiting for the suppliers to do it for us, and then we can buy it. That's a good question. There's actually quite a lot of them. I'm going to name one that maybe you haven't heard that much before, and it's quite specific actually to Lightyear maybe, and that's keeping the height of the pack down. So we are using 21700 cells, and for us the front passenger is actually sitting on top of the battery pack. And he needs a certain height between his heels and hips to have a comfortable seating position. And then you need enough height between the seat and the roof of the car to and also for enough space to have a comfortable position. And the battery pack is actually limiting the height of the total height of that stack. It's actually in the equation. So the higher the battery pack becomes, the higher the person will sit, the higher the car will become, and thus the bigger the frontal area will be. So the height of the battery pack has a direct influence on the aerodynamics, which are very crucial. And what we see is that most manufacturers have a pack height of about 150 millimeters. And while the Lightyear 1 has a pack height of 90 millimeters. That's 60 millimeters on a width of about 2 meters, right? That you will never get back in aerodynamic performance. About 6% on aerodynamics that many other manufacturers will lose right there, just on the pack height. So that's one thing. Another big challenge is crash safety or safety in general of the pack. So you have to think about what happens if one of the cell vents. Where do the gases go to? How much of the gas will come in contact with the sides of the other cells? So how much will they heat the other cells up? And will they send the neighboring cells into thermal runaway as well? Or can we keep it confined to just one cell, which is basically the case you want to have? So you have to think about where's the CID in the cell, and where does the gas go, and can it also go to the side, and also where does it vent out of the rest of the battery? So lots of simulations done on this part actually to make sure that you don't have a propagation of the thermal runaway. Another important part is how to integrate the cooling. For the Lightyear 1, we need cooling and heating, but not that much compared to other cars. The heaviest use case for us is the fast charging at 1C. And that means that in our concept, we have a double bus bar design in the battery. So all the battery cells are, usually you see battery cells from the one cell to the next cell, they are, one is with a minus on the bottom and a plus on top, and the next one will be the other way around, so that you can easily connect them in series, like that. And what we did at Lightyear, we have this double bus bar design, that where we put neighboring cells in the same orientation, with and then we have we contact the cell on the negative terminal on the edge around the positive cap, and then we go from that edge to the next cell. We go a little bit up, and then down again in the middle to the top cap. So you have, and then the next bus bar will be around that as well. And that way we can use the bottom cap of the cell as the thermal interface. So all the bottom cells are connected to a cooling plate with a thermal paste on the bottom, and that makes the total stack up of the battery very simple, very easy to assemble, and also quite efficient in terms of how many parts you need and the cooling, and that you don't have to weld on two sides as well. You just have to weld on the top side. It starts again at the efficiency part, because the car is very efficient and you still want to provide quite a bit of range. The battery is relatively small with 60 kilowatt hours. But because the range is big, you can calculate back that actually the C rates on the battery are lower as well. So that's strategy number one. Low C rates because the car is very efficient. Secondary, we have the solar panel continuously trickle charging the battery. So that also helps a bit, that you first of all compensate for that discharge, and you're charging very, very slowly, which is also very good for the lifetime in that sense. You're continuously charging a little bit. Then you indeed have oversizing and limiting the depth of discharge. If we look at that, then ideally that's something you want to avoid as much as possible because you're carrying extra weight that's not doing anything in the car. However, you do have to oversize a little bit, mainly because the power you can draw in the most extreme lower state of charge and is limited. So you do need to oversize a little bit. Then in terms of limiting the depth of discharge, you want to do that for lifetime quite a bit, but for the user, you're basically cutting off range. If you limit 5% depth of discharge, you have 5% less range. So the strategy in Lightyear is to let the user make his own informed decision as much as possible, because 99% of the time you don't need the range that the car has. You won't use the 725 kilometers every day. Usually you'll just drive 15 kilometers to work and back. So we will advise the user to only charge to, let's say, 80%, and only if they really need more, they can adjust somewhere on the screen the charge limit and say, okay, now I want it really to 100%. And also we will advise the user to start charging before the battery is completely empty. So in that way you will limit the depth of discharge as much as possible in practice, but the user has the option to override when he wants to really go from to the extremes. And if he doesn't do that too often, he won't compromise the lifetime as much. If we look at fast charging especially, then yes, definitely. That's actually the heaviest use case for the battery that we have in the car. It's a heavier use case than full-blown acceleration, for example, mainly because it takes so long. If you're charging for half an hour at 60 kilowatts, that's the heaviest thermal load that the battery will encounter during normal use. So definitely the thermal management system is then activated. I could also say it in another way: the thermal management system is always activated, and it's just monitoring the battery and then deciding what's the most efficient way to deal with this. So the thermal management system in the Lightyear 1 actually consists of a coolant loop and a refrigerant loop. The refrigerant loop is basically a heat pump that can work both ways actually, if you either need to heat or cool the cabin, and also depending on the outside temperatures. So also in the winter you can still use it as a heat pump to get extra heat into the cabin and to the battery. And then there are multiple interface points actually, or there's one main interface point actually between this refrigerant loop and this coolant loop. There's a heat exchanger. And we can route, depending on the conditions, we can route this in different ways. So we can use that heat exchanger, for example, to get heat from the motors and the inverters and the battery towards the cabin. Or we can also use it to, when we use the heat pump in the refrigerant loop, use it to actively cool the cooling fluid and use that for extra cooling for the battery and the motors. We can use the heat from the motors to heat the battery, or it really dependent on the situation. You want to find the most optimal mode, and basically it's done by routing both the refrigerant and the fluid depending on what's happening in the car. And basically you just look at what's the temperature outside, what's the temperature of my motors, what's the temperature of the battery, what's the temperature in the cabin, where do I want them? So heat needs to go from A to B. Now put all the valves in the position that's what happens. So if we look at the expected lifetime, we initially set the requirement at 80% state of health after 200,000 kilometers. The first test that we've been doing actually showed that we can achieve quite a bit more. So we're looking now at about 90% state of health after 400 cycles, which corresponds to about 300,000 kilometers. So that's roughly the expected lifetime.